So calculations involving balanced equations. Balanced equations show the relationship between the amount of product formed and the amount of reactant used. To balance an equation, you need to make sure you've got the same number of each type of atom on each side of the arrow. This is because we can't just magically produce atoms. We have to put them in to get them out. We're just changing the formation of the bonds. We're not actually changing the atoms. So in this example, we've got carbon reacting with hydrogen gas to form methane. So our carbons are balanced, we've got one on either side, but our hydrogens, we've got 2 here and we've got 4 here. Now hydrogen is a diatomic gas. It has to exist as H2. So we can't just change this 2 to a 4 and be done with it. What we've got to do is we've got to say we now need 2 molecules of hydrogen to make 1 molecule of methane. And how we do that is by putting a number 2 in front of it. And now we're balanced. We've got 1 carbon reacting with 2 molecules of the hydrogen gas to form 1 molecule of methane. So if you want to try these, you could pause the video now. I'll give you a second to do that. Okay, let's see how you got on. So for the first one, we've got nitrogen gas reacting with oxygen gas to produce nitrogen dioxide gas. Now the nitrogen, there's 2 nitrogens here, but there's only 1 on this side, so we times this by 2. By putting the 2 here, we're timesing the whole nitrogen dioxide molecule by 2, which means we've also times the number of oxygens by 2, which means we've now got 4 oxygens in our products and only 2 in our reactants, so we need to times our reactants by 2. It is worth saying that there is other ways to do this example, and it wouldn't be wrong to balance it as 0.5 into plus O2 gives O in O2. That's not wrong, it's just a different way to write the balance, and actually the numbers, the ratio is still the same. So for our second example, you've got calcium carbonate reacting with hydrochloric acid in a neutralisation reaction to form water, calcium chloride and carbon dioxide. The calciums are balanced, 1 on either side, the carbons are balanced, 1 on either side, the oxygens are balanced, 3 here, 1, 2, 3 here. The only thing that's not balanced is the hydrogen chloride. So hydrogen, 1 here, 2 here, chlorine, 1 here, 2 here. So all we need to do is put a 2 in front of that. For the third example, this is a combustion reaction, combustion of hexane. So we've got 6 carbons on this side and we've only got 1 here, so we need to times this by 6. And for hydrogen, we've got 12 here and we've got 2 here, so we need to times this by 6. Now by doing this, we've really changed the number of oxygens in the products, so we need to work this out. We've got 6 times 2 here, so we've got 12, and then we've got 6 times 1 there, so 12 plus 6, so we've got 18 oxygens altogether on this side. And we've got 2 here, so we need to times this by 9, so that overall we get 18 on the reactant side. So using these now, we can look at mole ratios, and mole ratios is how we would actually use the balanced equations in a calculation. So to find the mole ratio of nitrogen to oxygen, we're looking at these numbers in front of the chemicals. Now, if there's no number, that means 1. Chemists don't write 1, the number 1, as you know from writing formula. So if you don't see a number, it's 1. So nitrogen to oxygen ratio. So in this example here, we've got 1 nitrogen to 2 oxygen. And that's our mole ratio, written just as 1 to 2 mole ratio. Next example, you've got the mole ratio of hydrochloric acid to calcium chloride. So this time we've got a 2 HCl to 1 CaCl2, which is a 2-to-1 mole ratio. It's important to note the difference between these. They are not both the same. So a 1-to-2 mole ratio is not the same as a 2-to-1 mole ratio from the point of view of we'll be doing a different thing with it when we come into the main calculation. So hydrochloric acid to calcium chloride gives us a 2-to-1 mole ratio. But if we were doing the ratio of calcium chloride to hydrochloric acid, that would be a 1-to-2 mole ratio. And you need to make sure you look at what it asks you in the question before you write it, for the way you write it out. So, third example, find the mole ratio of oxygen to water. So here we've got 9 oxygens, so 9 oxygen to 6 water, and as scientists we would simplify that as much as we could, so we would make it a 3-to-2 mole ratio. It is possible that you could just be asked for the mole ratio as a question on its own, but it's more likely that you would then put that to use in an actual question. So here's an example. So propane combusts in excess oxygen to form 66 grams of carbon dioxide and some steam. Now, I've given you the GFMs there. They're both 44, which is just a coincidence. So it wants to know what mass of propane was burned. So the first thing we do is we balance the equation. So in this example, there is 3 carbons on this side and there's only 1 on this side, so we need to times this one by 3. And then there's 8 hydrogens here and 2 here, so we need to times this by 4 to give us 8. Overall, that gives us 3 times 2, which is 6, plus 4, 10 altogether oxygens. So we need to times oxygen by 5. Now, the question's told us that the oxygen's in excess. That means we don't use it in our calculation. Basically, it's been done in air and there's as much oxygen as the reaction required. What we're looking for is the carbon dioxide and the propane. So we know the carbon dioxide and we want to work out the propane. So what we would do is we would write it as so if we want to write it as a mole ratio, we could write it as 3 CO2 to 1 C3H8. So then we find out the number of moles of carbon dioxide. So we know the GFM and we know the mass. So to find the number of moles, we're using our original triangle. Number of moles is mass divided by GFM, which is 66 divided by 44, which overall gives us 1.5 moles. So that's how many moles of carbon dioxide we've got. Now we need to use our mole ratio to find out the number of moles of propane we've got. So it's a 3-to-1 mole ratio. So that means that we're going to have to divide 3 carbon dioxides gives us 1 of these. So if we've got 1.5, we need to divide it by 3 to get the number of moles of propane. So dividing that by 3 is going to give us 0.5 moles of propane. And that's linking to that equation there. So we've got that, the mole ratio coming down there to then become 3-to-1 gives us 1.5 to 0.5. Okay, so that's what the mole ratio is used for. And then using this number of moles, we can then find out the mass of propane. So we've got the number of moles. Mass is number of moles times the GFM. So we've got 0.5 times 44. So it's 22 grams of propane that would burn to produce that much carbon dioxide. So here's another example. You might want to pause again so you can try it yourself. Okay, so calculate the mass of silver which will be produced when 3.17 grams of copper reacts with excess silver nitrate solution. So this has already been balanced for you, which helps. So you've got your copper and your silver. So the mole ratio to start with then is 1 copper to 2 silver. So we can work out the number of moles of copper because we know the mass and we know the GFM back to our data book for the GFM of copper. Copper's a metal, so it's literally just straight from the data book, 63.5. So we've got number of moles is 3.17 divided by 63.5, which is 0.0499. That's rounding it a wee bit from your calculator. You don't want to round it any further than that. I definitely wouldn't round it to 0.05 at this point. You then need to use your mole ratio. So you've got a 1 to 2 mole ratio, which means that 0.0499 of copper, you need to times that by 2 to get your number of moles of silver that that's going to react with. So when we times it by 2, we want to keep it non-rounded still until the very end if you can. So then it's 0.0998 of silver. So we use that in this equation. So mass is number of moles times GFM. So we've got 0.0998 times the GFM of silver, which again, silver's a metal, so it's just straight from your data booklet, and it's 107.9. So then that gives us 10.7682 grams, which we would then round at this point to 10.8 grams of silver. So it asked us to calculate the mass of silver which would be produced, and we found it to be 10.8 grams.